Okay, we're going to go over the heat transfer problems, make whatever corrections you need to, because this one is not going to be for points, but we are going to do a few more problems after this that we'll be checking. So make sure you know how I came to these answers, and of course talk amongst yourselves if you need to after watching some of this. Okay, so first of all, number one, describe what's happening to water molecules when a 25 milliliter sample is being heated from -40 up to 0, so including attractions and organization. So from -40 up to 0, water is in its solid state, it's ice. So the only thing that can happen is the molecules can vibrate, okay? And then as you're going from -40 up to 0, that vibration just gets faster and faster. In terms of attractions and organization, they stay very organized, very fixed in place because they can't flow. They're not liquids yet. They are moving faster and faster, but their attractions, their hydrogen bonds, are keeping them in those fixed positions. Now, you could also then say that at 0, they begin to melt, and that's going to change things. That's going to cause some of them, not all of them, but some of them to have enough kinetic energy to actually break free and start to flow and change positions. But if you simply said that the vibrating particles were vibrating faster and faster from -40 up to 0, that would be good enough because I really didn't specify that melting was going on. Okay, then we get into our first calculation. So this one, we have water, 4.05 grams of it, cooling way down from 2010 degrees and condensing on a 28-degree metal surface. So we have to assume the final temperature of the water is 28 degrees. And so that means we have to cool the water, we have to cool the water vapor all the way down to the point where it would condense, which would happen at its boiling point. Then we have to condense it, and then it has to cool down some more. So let's take a look at what the heating curve would look like here. So the heating curve, and there you can see the math and the final answer, and I'll get to that in a second, but the heating curve, you have 2010 all the way down to the boiling point, because it would remain a gas all the way down to its boiling point, which would be 100 right here at this plateau. And then, of course, the plateau represents the condensation process, so like the opposite of boiling. Okay, so that's where you would use your heat of vaporization calculation. And then from 100 down to 28, it has to cool down some more, but this time as a liquid. So here you can see the 3 different steps being calculated. So first, part 1, we go from 2010 Celsius all the way to the boiling point, which is 100. So there you can see my delta T. I'm using my Q equals C M delta T equation. So my delta T is 2010 minus 100 degrees Celsius. My mass is 4.05. That's the only number that always stays the same for the whole problem. And then my specific heat, this is for water as a gas. So we go to our table and we find the specific heat of water vapor. It's 1.87. Multiply these together, we get our answer. We do want to round for sig figs there, which would be 3. Then the condensation process has our mass times our heat of vaporization. So make sure you use heat of vaporization because we're going from gas to liquid. Anytime we have gas to liquid or liquid to gas, we're using the heat of vaporization. And then we get our answer. And then we do the specific heat equation again for step 3, right? So but this time the specific heat is a bit higher because it's liquid water, 4.18. The mass remains the same. And remember, your delta T is not the total delta T from 2010 all the way down to 28 degrees Celsius. It's just that segment from the plateau down to the final temperature. So 100 degrees is where we were at the plateau, down to 28. And so once we get our answers, we just add them all up. And our rule for addition is our answer can only be as precise as the least precise number that we added up, which would be the hundreds place. So we have 24,800 joules. All right, next up, number 3. My answer is 11 milliliters, but here's how I got there. First of all, we're assuming sweat to just basically be water, even though we know there's some other salt and things in there. Sweat cools you by evaporating. So that is going to be heat of vaporization. And so we're going to use Q to figure out the joules. I'm sorry, to represent the joules. We know the joules, 25,000 joules. M is mass, and of course we have HVAP. Now we're solving for mass, and the reason we're solving for mass is because we're treating sweat like water. And since water has a density of 1 gram per milliliter, if I can figure out how many grams of water I have, that would be equal to my number of milliliters. So I simply go rearrange my equation to get mass, which would be Q over HVAP, 25,000 joules divided by 2,260, which is the HVAP of water. I just used it up above actually in the previous problem, and I get 11 grams, which I don't have to do any math for because the density of water is 1 gram per 1 milliliter, so it just becomes 11 milliliters. Okay. Number 4. This one, the heating curve is a little bit simpler. It's only 2 steps. So we have a 4.5 kilogram sample of iron. First thing I have to do is recognize that would be 4,500 grams. But I'm heating it from 25 degrees. So it's starting down here at 25 degrees. It's going up to its melting point, which if I look it up again on the table or right here, 1,538 degrees. So it's heated up to that temperature. Okay, so that's going to represent a difference of, so 1535 minus 25 is my delta T, going from here to here. And so this is a specific heat calculation. All right, so I have my specific heat of iron, which I look up on the table, my mass, which is just 4,500 grams, and my delta T, which I just described. And I get a pretty big amount, 3,100,000 joules. And it's such a big amount because it is a big temperature change, but it's also a big mass, right? And then the plateau, while we are melting the iron, that would be heat of fusion. So I did my mass, 4,500 grams times the heat of fusion for iron, which I looked up on the table, and I get this number. And then I just add them up, round to the nearest 100,000. And then for some reason on number 5, I repeated a problem that we had already done. So just ignore that one. Oh, and I never said for number 2, is it a positive or negative Q for the water and for the metal? So the water is cooling off, all right? So it's going to have a loss of heat. So technically, this Q that I calculated for the water would be negative, and then the metal would be positive because the metal would be gaining heat. Okay, so let's move on to number 6. Number 6, how many moles of silver could be melted using 465 kilojoules of heat? So the closest thing, I don't really have an equation that involves moles, but I do have one that involves mass, which of course if we have a periodic table we can then convert to moles. So I have mass equals Q divided by heat of fusion because we're talking about melting. And so then I just plug in my joules, which is 465,000 because I had 465 kilojoules. And then this number in the bottom comes from my table, my thermal properties table, and it's the heat of fusion for silver. It's only 88 joules per gram, so it's pretty small heat required per gram to melt silver once you get it to its melting point. And so then I just divide, and I get 5,280 grams of silver. And using the periodic table, I can easily convert that to moles, and I get 48.9 moles of silver. All right, number 7. So this one is a long one. This one requires 5 steps. And the reason it requires 5 steps is because we're starting below the freezing point of water and we're going to all the way above the boiling point. Okay, so you've got all 5 parts of a heating curve that you could possibly have. So I'm not going to go through every single number with you, but just keep in mind steps 1, 3, and 5 involve specific heat because they involve temperature change. So that gives us the Q equals C times M times delta T. Make sure you use the correct specific heat. So step 1 would be water as a solid. Step 3 would be water is a liquid, and step 5 would be water is a gas. So make sure you use the proper specific heat. Other thing I'll remind you of is only use the delta T for that part of the curve. So for part 1, we're only going from negative 14 up to 0. So that's a delta T of 14. I wouldn't want to do 124 minus negative 14 and use that delta T every time I have a delta T, because that's not, wouldn't be accurate. We only want the delta T for that part of the curve. Okay, and then we get into some conceptual questions to finish things up. The plateaus on the heating curve are where we have phase changes, and we discussed in class that just simply means heat is being added, that's melting or boiling, or it's being released in the process of freezing or condensing. Number 9 says substance A is a heating curve with a longer plateau than substance B. So at the molecular level, what does that mean? Probably means that substance A has stronger intermolecular forces. So it takes more heat to break, whether it's hydrogen bonding or just really big molecules that have high London dispersion forces, or dipole, whatever, but substance A must have greater IMFs. Number 10, what would you expect to be true about the heat of vaporization of butane compared to water, and why? Well, I would expect the heat of vaporization of butane to be much smaller than water. And the reason is if you were to draw the C4H10 out in a Lewis structure, you would get a very symmetrical and non-polar molecule. And so non-polar molecules are going to have weaker intermolecular forces. It is quite a bit bigger than water, but still, it's a non-polar molecule, and so we would expect it to have a smaller heat of vaporization. And then number 11, why are heats of fusion generally smaller than heats of vaporization? In other words, why is this plateau smaller than this plateau? Because when we melt something, which is what we have with heat of fusion, we're really only allowing the particles to flow, but the intermolecular forces are still taking over and holding them close together. When we boil something, we are completely separating those particles, and that takes a lot of heat. So pause, rewatch, I'm sorry, I guess don't pause right now, but rewatch whatever parts of this that you need to, because you will have another assignment where you're doing some of these heat transfer calculations.